Where are we going? Well, we're splitting the course up into 4 portions. So the first 3 weeks, and these roughly are about 3 or 4 week segments, the first 3 weeks we're going to do an algebra review and do some very basic things with lines. And lines are another way to say this is linear functions. These are very, very useful functions. Among other things, it's the kind of functions that, as humans, we're really good at. We're really good with lines because lines are flat, and our brains like flat things. Then we're going to transition, and in the second part, we're going to talk about functions, properties of functions, and introduce some very famous functions. The previously mentioned exponential function, logarithm function. And then we can take these and apply it to finance. Things like saying, what's the future value of an investment, or what's the current value of an investment? We then are going to switch gears and go into matrices. And matrices are essentially a collection of linear equations. And there's a lot of fun things you can do with them. We'll spend a few weeks talking about them. And then the last part, we're going to do counting and probability. And so you might say, wow, there's a lot of material here. And that's true. It's going to be fun. So in some sense, we're going for breadth. We're going to see a lot of different ideas. You could pick any one of these topics and make a whole semester course out of it. But we're just here to sort of help develop some mathematical intuition, some understanding. I have this note here. We want to help you learn how to think. It's a really important tool. Learning how to think is so useful. And because a lot of you are probably bound to go into business, and you want to be able to know if somebody comes to you with a crazy idea, is it true? Is it reasonable? Or is it crazy? And trying to think of the polite way to say this. You want to know if somebody's full of hot air, so to speak. All right, excuse my language. And you might say, well, that's in the future. But, it's kind of interesting. I've been looking at all these tools coming out with AI. And I think you need to learn how to think now. Because the thing is, AI will always give you an answer, and it will always be confident about it. It doesn't mean the answer is good. So you need to learn to not trust things blindly, but rather to think critically and say, hold on, is this right? Or is this making a mistake? Because mistakes can be costly. All right, last thing. Some advice. Use your resources. You have a lot of resources available to you. There is an SI associated with this course. Not with this particular section, but with this course. You can check to see when they're available. This SI stands for supplemental instruction, and that can be a great tool because you'll have somebody who's been through the course before who gives you information. You have office hours and help hours. These are great. You can go get your questions answered. It's wonderful to get your questions answered. You have lectures. You should attend lectures. Now, you may have noticed attendance is not part of your grade because we're not taking attendance. It doesn't mean you should skip lectures. We think there is value to be had in being here. So please come. Please come. That's a good resource. There's online materials. We've pointed some of them out. And, of course, you can study with others. You may remember classic movie scenes where the professor will say something like, turn to your left and turn to your right. And then they try to scare the students. I don't think that's what we need. You should turn to your left and turn to right and say, look at all these people who also want to pass the class. We can all pass. There's nothing that says we have to fail students. And you can work together. You can study together. You can also seek out tutors. Tutoring can cost money, but I do think that there are some options which might be free through the Academic Success Center. All right, so use your resources. Stay engaged. Come to lecture. I know I've said that, but it's a good piece of advice. Come to lecture. And ask questions. I really appreciate people asking questions. And because I want to make sure you understand. My goal is not to prove to you I'm a smart person. My goal is to help you understand that you're a smart person. And so ask. Take notes. Think about things. I like to, when I'm going on a walk, think about what I'm learning. And, my goodness, walking is a great time for thinking. Be persistent. I'll probably talk about this more later this week, but a lot of people will run into early setbacks. Maybe they make a mistake. Maybe they got 9 instead of 10 on the homework. I don't know how much the homework is worth, but let's say it's 9 instead of 10. And they'll just be frustrated, and they'll stop putting effort in. Over time, this builds up. And the outcome is not good. Be persistent. You control your destiny. Invest in yourself. You're worth it. Keep going. When I say start early, that means even though things are due Monday, that doesn't mean you have to wait till Monday to start. You can start the homework sooner than that. And the quizzes, I would say probably maybe even Saturday or Sunday, do your first attempt. Give yourself time to think about what happened. And the last thing, of course, is ask for help. There's nothing wrong with asking for help. It's not a sign of weakness. A lot of people need help, and you're not alone. All right. Well, with that, any questions about the course, where we're going, what you need to do? Okay. You might be wondering why I had you grab a rubber duck. Just want to talk a little bit about something called rubber duck debugging. This is used by computer programmers. And when they're stuck trying to solve a problem, one of the things that they have learned to do, and I'm not saying they all do this, is that they'll grab a duck and they'll go to their duck and they'll start explaining to the duck, here's what I'm trying to do, and they'll start explaining the process step by step. I did this so that this will happen, which causes that. And what happens is, in the process of explaining what's going on, they understand what happened. It's not that the duck explained it to them, but rather the art of talking it out and trying to explain what's going on help them to understand the pitfall. And so that's why I want you to have a rubber duck. You don't have to talk to the rubber duck if that makes you uncomfortable. But maybe find a person. People are great to talk to. And it's wonderful because one of the things that you'll discover is that it's hard to find your own mistakes, but it's not so hard to find others. And so if you work together, then you can help each other out. So that's a technique you can have. What's our goals for today's lecture? Well, we're talking about two things. Numbers, some very basic of numbers, and rules for working with numbers. So, for numbers, we'll start with the number line. Now, if you go back in the history of math, we started with the ancient ancient Greeks. And they were the first ones to really start delving into mathematics. And for them, everything that they thought about was in terms of geometry. Lines, circles, that was the underlying philosophy. That's what they tried to do. So they said, okay, well, how can we understand numbers? We'll think about things as a line. Now, one thing that you can start with is you can say, well, I'll start with a point. I'll call it my first point. And then I can say, well, there's another location some distance away. That's my second point. And then I can just copy the same width. And so I get these collections of points, 1, 2, 3, 4, 5, and so forth and so on. And these were called the natural numbers. They're also called the counting numbers. And what do we see? Well, this is, whoops, how do I mark this? Yeah, N, there we go. Wait, is that an N? I feel tired. All right, yeah, that's probably an N. It's close enough. No, it's the wrong N. I was trying to remember how to write a bold N. There we go. Natural numbers. And so this is the set 1, 2, 3, so forth and so on. All right. Great place to start. Everybody's comfortable with that. Then they said, hold on a second. We can go in the other direction. So we should anchor it. We'll introduce a number called 0. And we'll think of this as the origin. And then we'll go also the other way. Now, we run into a problem. We can't have two things described by one. So what's the solution to our problem? Yeah. So they said, hey, we should have an orientation of this line. We will have a positive side and a negative side. So when I think about positive and negative, I'm really thinking about that being a orientation or direction. So in the positive direction, in the negative direction. So we have a -1 and a -2. And this leads us to what are called the integers. And oftentimes denoted with the Z. And there's a lot of them. So going off in both directions, positive and negative. All right. Well, of course, people were not quite satisfied yet. Said, all right, we've got some points here, but we have these big gaps. And they said we should mind the gap. We got to fill things in. Okay, so how can we do that? Well, they figured out a way to do it by looking at ratios of integers. So you get the rational numbers. And rational coming from ratio. So this is P over Q. This is an integer upstairs. This is an integer downstairs with one caveat. It can't be 0. We don't like to divide by 0. Divide by 0 is a dangerous thing. Be smart, don't start. Now the good news is this filled in a lot of numbers. So you could have things like a half, or you could have something like, 21 fifths. And it turns out there's lots and lots of rational numbers. In fact, they're all over the place in some sense. So, great. Now there was the question, do we have them all? Because just like in modern day, we have the goal, got to catch them all, right? The question is, do we have all the numbers? Well, not so obvious, and there's a lot of story that goes into that, but it turns out that there were other numbers left over. So these are the irrational numbers. And these are basically real numbers that cannot be written as a fraction. All right. Now, what's an example? Well, the earliest one that they figured out is over here, called square root, oh, no, not over there, excuse me, over there, square root of 2. Square root of 2 is not a rational number. There's no way to write that as P over Q. And they figured this out, the Greeks figured this out. And of course, once they did, it was all very hush-hush. Don't tell anybody this, because it's going to blow their minds. They're not ready for this knowledge, that there's other types of numbers out there. Now, it turns out irrational numbers, there's a lot of them. And there's some very famous ones. You have pi, a little bit bigger than 3, a little bit less than 3. You have what's called e. Now, pi, anybody know some digits of pi? Yeah. Cosine, secant, tangent, sine, 3.14159, right? Yes? Anybody know e? That's all right. We'll know it. There's even a chant for that one. Come on, exponentiate, 2.71828. And then by coincidence, it's 1828 again, but then it's something else. All right, so these are your numbers, and these are the ones that we get to work with. What can we say? Well, the rational numbers, I should have made a quick note here. There is some notation for rational numbers. These are Q. So if you were to draw sort of a layering, you have your natural numbers. Why am I having a hard time drawing natural numbers? Then they're inside the integers, which are inside the rationals. And then, split off, separate from the rationals, you have the irrationals. And then all together, this makes up your real numbers. So this is sort of how they piece together. And this is, of course, there's a lot more to the story. And things can get a little bit more complex. But that's a story for a different time. All right. So these are our basic numbers. All right, well, what can we do with these numbers? We want to be able to do some operations. And there's two big operations we like to work with. We like to do addition and multiplication. And a lot of these are things you just sort of know are true implicitly. And we have names attached to it. I wouldn't worry too much about memorizing the exact names. But just for reference, what do we have? Well, we have what's called associative. And you have here, you can see what it says for addition. First add A and B together, and then add C, is the same as adding A through the result of adding B plus C. Well, what is that telling us? Well, it's telling us that we can choose a little bit in the order of how we do our operations when it comes to addition. Now, you have to be a little bit careful. We'll get into that. Multiplication, very similar. If I take A times B and then take the result of that times C, that's the same as taking A times the result of B times C. All right. You have commutative, which basically says, hey, A plus B is B plus A, and A times B is B times A. And you're probably thinking, of course, that's how it always is. But I will say, you can get to points in math where you're dealing with different types of things other than numbers, but you still have notions of addition and multiplication where these things start to break down. So we do have to explicitly say what we can and can't do. We have what are called identities. So there's the additive identity, which is called 0, the multiplicative identity, which is called 1. And essentially, the idea of the identity is it's the thing that leaves things alone. If I add 0, I don't do anything. If I times 1, I don't do anything. And these are useful things to be able to do. So one of the ways that mathematicians oftentimes sort of try to manipulate expressions is they say, well, is there a good way to add 0? Is there a good way to multiply by 1? And you might say, well, what do you mean by good? Well, first off, adding 0 and multiplying by 1, we haven't changed anything about the net answer, but we've changed the way to express the answer, and that can be valuable. On a side note, mathematicians love 0 and 1. There's a piece of advice for those people taking math classes, such as yourself, that when a professor asks a question, the answer tends to be one of three things: 0, 1, or written somewhere on the board. So there is a definite bias towards 0 and 1. We have inverses, and it's kind of a weird way to say it, but what's our goal? For any number, I can find a number such that when I add it, I get 0. How do we do it? We take the negation. So if I start with 5, and I want to get 0, what do I need to add? Add negative 5. If I start with negative square root of 2, what do I need to add? Square root of 2. So you basically change the sign. So one way you can think about it is I like to think about a number can be like, if I were to start at 0 and move that amount, where do I end up on the line? So I can think of the negation as saying move in the other direction. For multiplication, there's a similar idea. If I have a number non-zero, doesn't work for 0, then there's some other number I can multiply it by and get 1. And essentially, it's the reciprocal. And there's some notes here. If we're talking about subtraction, it means add the inverse. If we're talking about division, multiply the inverse. A few other notes about 0. If I multiply anything times 0, I get 0. If I take something and divide by 0, I get something that's undefined. Don't divide by 0. Don't want to do it. And this is a nice one. If I have two things, A times B, and the result is 0, it's only possible if one of those two things is 0. Now, this is a nice thing, and we're going to use that. It says, hey, if you can turn a complicated expression into a product of two smaller expressions equaling 0, then you can break it into two smaller problems. Math, oftentimes the goal in math is just to say, let me simplify. Yes, we're trying to solve problems, the way that we solve problems is we make them into simpler problems. Step by step, try to make things simpler as we go along. All right, last property to mention on this page, the distributive property. Now, this is an important property because it combines both multiplication and addition. And so, how does it work? It says, if I want to take A times the product of B and C, I can distribute the A. So you can think of it as like the A comes through. So I'm going to have A times B plus A times C. Now that's distributing in from the left. You can also distribute in from the right. So if I take the sum of A plus B, figure that out first, and then times it by C, that's equivalent to taking A times C and adding that to the result of B times C. So we can do distribution. I saw an accounting professor a few days ago, and I was mentioning I was teaching this class to business students, and she was like, 80% of them, this is the number she gave me, 80% of them don't know how to do the distributive rule. So let's not be that 80%. It's very important to learn. It shows up a lot. Now, I'll say a few pieces of advice. We'll call these a pro tip. Watch out for the minus sign. Oftentimes, one of the biggest mistakes that gets made with distributive rules is the minus sign. So be careful. Make sure you get that minus sign applied correctly. And another good thing to keep in mind is that parentheses are friends. You want parentheses. They will help guide you to make sure you understand what's going on. Now, as an example, suppose someone says to you from across the office, "Hey, what's 2 plus 3 times 5? What's the answer?" "2 plus 3 times 5. Could be 25, could be 17. The answer is we don't know because he didn't pose the question well. Because when you say 2 plus 3 times 5, you could have meant 2 plus 3 times 5, in which case the answer is 17, or you could have meant 2 plus 3 times 5, in which case the answer is 25. So there's these ambiguous expressions, and you'll see these from time to time. People will post this on Instagram like, 8 out of 9 mathematicians get this wrong. No, 8 out of 9 mathematicians don't play the game because you have ambiguous expressions. So be careful, respect parentheses. They are your friends. They will help you. Okay, a few other properties, and we'll try to go over these a little bit quickly here. We have some things related to negation. When we talk about negative A, you can think of that as negative 1 times A. And then negative of negative A is A. Oftentimes you think about it as that, if I take negative A times negative B, it's just the same as A times B. Multiplying 2 negatives makes a positive. 2 wrongs make a right. No, that's not true. That's not true. How should we think of it? Why, when we put a negative and a negative, we get back to positive? What is negative doing? Think of orientation. You have our positive direction. You have our negative direction. So, A negative, it's like flip around. Go the other way. What happens if I start and I do two negatives? 1, 2. Flip, flip. I'm back in the way I started. So that's how I like to think of multiplying two negatives gives us a positive. All right. So, if we have a over b, that's equal to c over d, if and only if AD equals BC. There's sort of this implied no division by 0. This is called cross multiplication, or cross multiplying. It's a great way to help simplify expressions. I'm of belief fractions are dangerous. I've lost too many points in my life to fractions. I don't want to go lose that again. If I have a times c or b times c, that's the same as a over b, and there's sort of the notion, oh, you can cancel off the common factors. If I want to divide by a fraction, multiply by the reciprocal. So division by c over d is the same as multiplication d over c. And one other thing here is if you're going to add fractions, get a common denominator. And fractions can be very confusing. There was a time, this was probably about 30, 40 years ago, when one of our big burger chains, I think it was McDonald's, they were like, we've got the quarter pounder. And so another chain came out and said, okay, we're going to make the third pounder. Now, what happened? Well, it turns out people were bad at fractions, and they said 1/3 versus 1/4. Well, 1/4 should probably be bigger, because 4 is bigger than 3. No, it's not how fractions work. So be careful, be careful. All right, we have a few minutes left. Let's try some basic statements here. Are the following true or false? Is A true or false? False. You can't just cancel it with a little bit downstairs. You have to be careful. Addition and multiplication don't get along perfectly, so you have to be very careful when you mix them. Is B true or false? True, but here's the thing. Why is it true? Some people might be tempted to do what? Cancel the 6's. Can you cancel 6's like that? No. So I bring this up just to say, be careful. Something can be true, but they can give you a wrong justification and can be very misleading. Part C, true or false? False. What's wrong here? The negative comes through and distributes. So it should have been 7 minus 6 plus 12. All right. D, true or false? False as it is written. What's wrong with this? One of these has to be 0. It doesn't mean the first one has to be 0. If we had added the phrase, or x minus 5 equals 0, then it would be true. All right, that's it for today. We'll pick up again next time.